Hello, hello. Okay, so I'm making this video to go through some of the instruction tracing that we've done in lab because I feel like it's helpful when we do it in lab, but then I upload our annotated notes and the PDF just kind of looks messy. It's a lot of colors, a lot of writing, and it's hard to follow sequentially, which is really important for tracing. So I thought I'd make this video, go through it, and hopefully clear up some confusion that we have been having. And also, this could be a good reference when y'all are doing the microcode in Project 2. Just something to look back on and help you trace instructions. Okay, so we are going to, oh, if it'll let me. There we go. All right, first thing is going to be fetch. And we're starting with fetch because this is our first macro state. And when I'm thinking about fetch and tracing in general, the first thing that I want to do is think about the big picture of what this does. So with fetch, we know that we have something in our PC, and our PC holds the address of the next instruction that we want to execute. And I know that eventually we want to have the contents of that instruction, so not the address, but the actual contents in our instruction register down here, that little square. And we also want to update the value of our PC. So when we're running a program, we won't just want to do the same instruction over and over and over. We want to move on to the next line or, the one after that, and so on and so forth. And so we're also going to be incrementing the value in PC. So when we are doing this, we can break it into three different clock cycles, three different little microstates here for fetch. And for the first one, we are going to say we want to take this value that's in our PC and we want to use it as an address for our memory. And to do that, we need to get that value into our MAR. So we have our PC here. We want to get to the MAR. Okay, we're trying. What's stopping us? Gate PC. Okay, so we know that gate PC needs to be 1. Okay, got this. We're traveling. Gate PC's 1. All right, now we got it onto the bus. We're going to drive down. Oh, and we want to get it into the MAR. What's stopping us? It would be this thing. It's how we load a register. Okay, so we're going to do the LDMAR. We know that needs to be a 1. And remember I said that we also wanted to update the value of our PC. So while it's not necessary, you could do this technically in any of the clock cycles of fetch. It's kind of customary, and especially in this class, this is what we do, is we do it in this first cycle. So we're going to take the value of PC, send it along down this line. Okay, go through that adder and through the PC mux and up into the PC. And so to do that, we need to make sure our PC mux is a 0, 0, and then PC is still a register. So we want to make sure we have load PC is also 1. Okay, boom. There is our first microcode for fetch. And here I'll write the little purpose up here. Do MAR, and we want to load that with the contents of the PC. Okay, and we also want to do PC plus plus, increment the PC. All right, so now with fetch 2, we know we have our address down here in the MAR. We want to get the contents of that from memory and then put it into our memory data register right here. Okay, so we can think of this as we want to do MDR mem. That means we're accessing memory. And within these brackets, it's going to be the address we're using, which obviously is held in our memory address register. Okay, so I will use, how about yellow, to trace this one. So we have this, got our address in the MAR. We're going to access memory, and then we're going to put it in the MDR. So when we're addressing memory, or when we're accessing memory, excuse me, we need to make sure that we have memory enabled, set that as 1. And then when we want to actually get that value into our MDR, we're going to have to load MDR. MDR is a register after all. Okay, so now we got the contents of the instruction itself. It's sitting in the MDR, so we're almost there, but we're not quite done yet. Last thing we want to do is we want to have the contents of this actually end up in the IR up here. So not going to be a long trip, but let's say we want to have IR, and we want to load that with whatever is in the MDR. I think I will use green here. All right, so that's going to travel. Oh no, what's stopping us? Gate MDR. Okay. That needs to be 1. Okay, so now that tri-state buffer is 1, it's going to pass that value through. Short trip on the bus, and we're going to make it to the IR where we have to load IR. Boom. Okay, so that is what our fetch looks like. I hope that's clear. And so we will go on to the second macro state, and that is decode. So decode, we ended fetch knowing that we have the contents of our instruction in the instruction register. So down here, decode, we can think about as sending the contents of that into our finite state machine, into the brains of our microprocessor. And the FSM is then going to determine which instruction we fetch. So whether or not it's it's a store, it's a load, it's an add, it's an and, it's a not, that sort of thing, because each will have their own distinct opcode. And the opcode, if we recall, first 4 bits of the instruction. When I say first, I mean most significant bits. And then that finite state machine is going to assert the relevant data path signals based on the current instruction, and that is going to start our execution. Okay, so once we get to that, let's talk about the types of instructions there are. There are 3 main classifications. First one being the operate instructions, and this is going to act on data held in registers, usually in our register file. And then the second operand could be another register in our register file, or it could be an immediate value contained in the instruction itself. And that immediate value will usually be in the least significant bits of the instruction. And it could be 9 bits, it could be 6 bits, and it could be 5 bits. Second classification is going to be data movement. So these are going to be like our loads and our stores, loads, stores, and these are going to move data around within our data path, and they're often going to go through and access memory. And if you'll notice, there are 3 of these. These are all loads, and they differ in their type of addressing mode. So this is going to be PC relative, this is going to be indirect, and this is going to be base register plus offset. And obviously same thing here. Third type is control. I don't think y'all have covered that in lecture yet, but control is just going to change the way our program executes subsequent instructions. So it's going to change the value in our PC, and we got branch, jump, jump to subroutine, and jump to subroutine via register. And we'll talk more about those later. I'm not going to go into it too much in this video, but after y'all do cover that in lecture, maybe we do another thing for that. So let's actually trace some of these instructions. First up is going to be add. So add, if we remember, it's one of our operate instructions. And when I'm tracing an instruction, the first thing I like to do is I like to look at the instruction and think big picture. Think, what does this do? So add, pretty straightforward one. I can think about what it does. It probably adds 2 things together. But if I wasn't sure, if I had no clue, if I was looking at it and I said, I have no idea what this does, a good resource for me would be the ISA for the LC3, the instruction set architecture, which is a PDF, and I think they included it in the project 2 files. So it should be a big PDF contained within that folder. And it's really helpful for getting information on what the instruction itself looks like, what it does, what are its operands, does it set the condition codes, does it not set the condition codes, that sort of thing. So looking at add, we know the big picture, it's going to take a value from one source register, and it's going to go through, and it's going to add with whatever the output of our SR2 mux then is. Going to take that result, and we're going to end up putting it into our destination register. And so add and our and also as well will vary in the sense whether they are taking something from an SR2, so whether they're adding SR1 plus SR2, or if they're adding SR1 to an immediate value, and that will be determined by the 5th bit, so this bit right here, and that will be used as a selector. So as you can see, if that is a 0, we are taking it from a second register, so in our register file, and if that is a 1, we are going to use assign extended immediate 4 bits from the instruction itself. So excuse me, 5 bits, it's 0 through 4. Okay, so let's go ahead and trace add. So first thing we're thinking is, I'll use maroon here, is we are getting SR1, and that's going down. Okay, pretty straightforward. We know that the SR2 mux will automatically pick something. In this case, because we have a 0 here, we are using SR2. Okay, so that's going to go down, going to be driven through that mux. ALU is going to need to perform one of its 4 operations. In this case, it is the add one. So it is ALUK. That is 0, 0 for the ALU. That value is going to be output of our ALU. Right now, what's stopping that from getting onto the bus? Our gate ALU, so we need to make that 1. Okay, boom, we're through. We're onto the bus. Driving back up and going down, and we want to load it into a register. But to do that, we know these are edge triggered, so we need to have our load register enabled as well, which would be a 1. And we're not done yet. It seems like we might be, but we also need to recall that add sets our condition codes. Okay, so we need to make sure that this value also goes up through here. It'll automatically go through the logic because this box is combinational. And then we want to store the value of that in our condition code 1 hot register. So we need to do load CC. Okay, so these are the signals that need to be asserted for add. They'll also be pretty similar for and. Just going to be a minor change with what's in the ALU, but yeah, hopefully that makes sense. Tracing one of the operate instructions. And next up we got load. Okay, LD. So again, like I said, with big picture, looking in the ISA, for load instructions, what we're going to do is we are going to calculate an address in memory that we want, and we're going to do that via summing an offset value and something from the adder address 1 mux. So right here, and we're going to do that addition in this adder. The address 2 mux is going to be choosing which of our offsets we want, whether it's a 6-bit, whether it is 9-bit, or whether it is an 11-bit offset. And then our address 1 mux is going to choose whether we want to use our base value being the PC, or if we want it to be something that is coming from the register file. And the way we calculate it, so all those options I just gave, it depends on the type of addressing mode that we have. And so the addressing mode is going to be like LD. We know that is PC plus offset. We know LDI is indirect, and we know this is base register plus offset. Okay, so with our LD, we know we are getting something. We are going to calculate an address. We want to put it in the MAR, and then we want to load that value from memory, get it in the MDR, and put that value into all the way up into our register file. Okay, so first clock cycle, we are going to calculate the address and get it into MAR. So I'll use my light blue again, and we'll say MAR, and we want that to be the value of our PC. And note that I'm doing PC, that's an asterisk, I didn't make that very clear. PC star, and this just means that it's our PC incremented, because remember back in fetch when we did the +1 up here, so that's what that means. That's PC +1, and we are going to do an offset of 9. Okay, so what we need to do is, remember we chose PC as our base value, so it's going to come up here, come all the way down, go into address 1 mux. So what our selector needs to be is ADDR1 mux will be a 0. Okay, and then we're choosing our offset. We see our offset 9 bits. Which one looks like it has 9 bits? Looks like this one. Looks like that needs to be 10. ADDR2 going to be 10. Okay, so now we'll have both of those. Let me go ahead and trace that. Going up, it'll be driven through this mux. These will go through the adder. Gonna go up into our memory address register multiplexer, and we know we want to send that value through. So let's pick 1 as our selector there. I'll do it down here. Mar mux needs to be 1. If we want to get that value, put it onto the bus. What's stopping us? Gate marmux. Gate marmux needs to be 1. Put it onto the bus, and then we're gonna go down into our MAR, and then we know how to load things into a register, which is just doing that load signal. Load MAR. Okay, so now we have the address that we want. We calculated it. We got it into our MDR, or excuse me, our MAR, memory address register. Now, next thing we want to do is get the actual contents of what's in memory at that address and put it into our MDR. So let's do our big picture. MDR is going to be mem of MAR. All right, and remember how we do that? It is pretty straightforward. I'll use yellow. Get the address, go through memory, and then put it into our MDR. So for that, we need, remember we're accessing memory, so we need to do memory enable. We're just reading, so read write still can be 0. And then we are going to load our MDR, and that is a 1. Okay, so now we have the relevant contents. We have what we wanted to grab out of memory. That's in our MDR. And remember our end goal, we wanted to get it back into our destination register. Okay, so final step, destination register is going to be the contents of our MDR. And also, our loads are going to set the condition codes. Okay, it's very important not to forget that. It's easy to forget. Just try to, make sure we stay 10 toes on that. All right, so we got our content in the MDR. We want to get it on the bus. Okay, what's stopping us? The gate MDR. Make that 1. Gonna drive it onto the bus. I'm gonna try not to overlap my maroon from clock cycle 1. And we're gonna go all the way up, all the way into our register file. And to load it into a register, we know we are going to need to LDREG is equal to 1. And remember I said we set the condition codes as well. So it's going to go through logic and it's going to be stored in our condition codes. Okay, so that's what you need to trace load. Hope that makes sense. I hope this video is somewhat helpful. And again, if y'all have questions, please let us know. Piazza, textbook, you could talk to me or Jack as always. So good luck. Hope this made sense. Good luck with homework. Good luck with project 2. And yeah.